Let's talk about CFDs for a moment. Computational fluid dynamics. It's where software emulates real-world systems and calculates the fluid dynamics going through that system based on a model that you give it. So for years, I've been doing CFDs. I just recently upgraded my hardware to a dual gold 6415 Xeon 78 core or 72 core processor with 512 gigs of memory and a massive amounts of video RAM of 38 gigs. This gives me a highly powerful machine to run the CFDs, and I use ANSYS, and I use OpenFOAM, and I use SolidWorks to do the CFDs. Now let's talk about some of the CFD characteristics. I usually get between 850 cells to 3.4 million cells, depending on the complexity of the model that I do it on. And I've done it on the 55-inch, or 55 millimeter, sorry, the 55 millimeter turbine. I've done CFDs on the 3-inch turbine, the 6-inch turbine, the 10-inch turbine, and the 13.3-inch turbine. And the reason why I run all these CFDs is to give us a round number of efficiencies and the way the efficiencies work. Let's marry that together. So the CFDs do something really special for us. It allows us to see via the calculation exactly how the CFDs interpret the efficiency for each one of those models. Now, for the big model, the 13.3-inch turbine, I get 42.5% efficiency. For the smallest turbine, I get 75% efficiency. Now, that is, in contrast, completely different than a standard turbine. A standard bladed turbine is actually opposite of that. The smaller you go, the lower the efficiency, 18 to 20%, whereas in the bigger turbine, you get 33%. This is very fundamentally strange because the smaller the turbine that I make, which is good, the higher the efficiency. Now, I've given you some of the efficiency numbers between 75 and 42.5 for the biggest turbine. But even for the biggest turbine, which is 1,000 horsepower, that turbine is huge. It's this big around. It's 13.3 inches. It weighs like 350 pounds. The thing is, it's a monster. But it runs on the exact same principle as the 55 millimeter turbine, which is the scallops with the jets. And fundamentally, I still get the same 130,000 RPM hurricanes on the outside of the scallops for the turbine rotor, which is where I extract all of my energy. Now, the CFDs also show us that it's laminar flow. That is very specific because it's hard to see that with empirical testing. Empirical testing is just when you're doing a physical test, which I've shown you already some of the physical tests that I've done. The CFDs show us the exact fluid dynamics and exactly how it functions within the whole turbine. And like I said, laminar flow is very important. Cavitation and swirls. The word I'm looking for is cavitation and turbulence. Cavitation and turbulence are very, very detrimental because they grab energy and they exhaust it without any work being done. That's why laminar flow is very important for this turbine, because it allows more of the energy to be used at the rotor. So now that we know what my efficiencies are for the small turbine and the big turbine and the in-between turbine, it gives us a scale. And that scale is very important for judging how well the performance is of the turbine from one size to another. I'm running out of topics here. So bear with me. We'll come back to this in a little while.